What if I told you the ground beneath your feet is drifting, reshaping continents, sparking volcanoes, and rewriting Earth's history? Stick around, because we're diving into the fascinating evidence behind plate tectonics, and some of it is hidden in ancient rocks, glacial scars, and even the ocean floor. Stay tuned to uncover the evidence behind plate tectonics, and don't forget to like and subscribe if you're fascinated by the forces shaping our planet. Welcome to the channel. Today, we're going to explore the trail of evidence that led to the revolutionary theory of plate tectonics, the idea that Earth's lithosphere is broken into plates that move across the planet's surface. We'll dive into fossil clues, glacial scars, ancient magnetic fields, and seafloor mysteries to understand how continents move and how science finally proved it. In the early 1900s, Alfred Wegener noted the striking fit between the coastlines of South America and Africa. While others had seen the resemblance before, Wegener took it further, proposing that the continents had once been joined in a supercontinent called Pangaea. But critics pointed out, coastlines are continually modified by erosion and depositional processes, and it is not possible to have a good fit today. The breakthrough came in the 1960s, when Sir Edward Bullard and his team used the edges of the continental shelves, and not the coastlines, and found a near-perfect fit at a depth of 900 meters. This submerged outline showed far more precision than Wegener's original fit. If continents were once connected, we'd expect their geological features to match up, and they do. The trends of several major mountain ranges also support this. These mountain ranges suddenly end at the coastline of one continent only to apparently continue on another continent across the ocean. One powerful example, the Appalachian Mountains in eastern North America, which run northeast through the US and Canada and abruptly end at Newfoundland. But mountain ranges of the same age and deformational style continue across the Atlantic in eastern Greenland, Great Britain, and Norway. Even though the Appalachian Mountains and similar-aged ranges in Great Britain are now separated by the Atlantic Ocean, they line up to form one continuous mountain range when the continents are placed together as they were in the Paleozoic era. The fossil record offers some of the strongest support for continental drift. Take the Glossopteris plant, a seed fern from the Permian era, whose fossils are found across South America, Africa, India, Australia, and Antarctica. Its large seeds couldn't have been carried by wind or survive saltwater, and the present-day climates of these regions are far too varied for it to grow across all those regions. This only means that these continents must have shared a similar climate at the same latitude as part of the same supercontinent, Gondwana. Even more compelling is the Mesosaurus, a freshwater reptile found only in Permian-aged rocks in Brazil and South Africa. It's highly unlikely this animal crossed an ocean of saltwater between continents, unless those continents were once connected. Similarly, land reptiles like Lystrosaurus and Cynognathus, which couldn't survive ocean crossings, have been found across South America, Africa, India, and Antarctica. These fossils, along with recent dinosaur discoveries across former Gondwana, make it clear life once roamed freely across what are now distant continents. The evidence from the late Paleozoic era, 300 million years ago, shows that massive glaciers covered much of southern hemisphere, including present-day India, Africa, South America, and Australia. Today, these regions lie near the equator in warm, tropical climates. Another astonishing discovery was that the glacial striations in their bedrock show that glaciers moved from the oceans onto land, something that doesn't happen. Large continental glaciers typically flow from land toward the sea, not the other way around. So, if the continents were always in their current positions, then how glaciers formed near the equator and moved inland? An unlikely scenario. Meanwhile, rocks of the same age in the northern hemisphere show no sign of glaciation. but show thick coal deposits formed from tropical swamps in places like the eastern US, northern Europe, and Asia. These swamps were filled with lush vegetation like tree ferns, which had no growth rings, a trait of plants from warm, stable climates. Wegener's solution? Reassemble the continents into a supercontinent, Pangaea. All the southern continents cluster around the South Pole, explaining the glaciers and their movement. At the same time, the northern continents shift closer to the equator, matching the evidence of tropical swamps and coal formation. This arrangement explains both glacial activity in the south and tropical climates in the north. Paleomagnetism is the study of magnetic signals preserved in ancient rocks, signals that record the direction and strength of Earth's magnetic field at the time the rocks formed. Earth acts like a giant bar magnet, with magnetic poles located near the geographic north and south poles. The geographic poles are located where Earth's rotational axis intersects the surface. The field itself is generated by the motion of molten iron in Earth's outer core. When lava erupts and cools down, it contains iron-rich minerals like magnetite. While the lava is still hot, above 585 degrees Celsius, known as the Curie point, these minerals don't hold magnetism. But as the lava cools and solidifies, the magnetite align with Earth's magnetic field and freeze that direction. So, ancient lava flows act like natural magnetic recorders, showing where Earth's magnetic poles were in the past. These rocks preserve what we now call fossil magnetism or paleomagnetism. In the 1950s, scientists studying paleomagnetism across Europe made a surprising discovery. The recorded position of Earth's magnetic North Pole, preserved in ancient rocks, appeared to have shifted over time. Over the past 500 million years, the pole seemed to move from a location near Hawaii to where it is today, near the geographic North Pole. A similar magnetic path was constructed for North America, and while both paths pointed in roughly the same direction, they were offset by about 5,000 kilometers. Then, around 180 million years ago, during the Mesozoic era, the two paths began to converge. At first, this gave the illusion that the magnetic poles themselves had wandered. But as paleomagnetic data from around the world were compared, scientists realized something important. The magnetic poles had remained relatively stable. It was the continents that had moved, making it only seem like the poles had shifted. When North America and Europe are repositioned to their pre-Atlantic configuration, their magnetic paths line up perfectly. This alignment provided strong evidence that the two continents were once joined and have since drifted apart, a major piece of proof supporting the theory of continental drift. Earth's magnetic field leaves behind a secret message in rock. As discussed earlier, basaltic lava cools and iron minerals like magnetite align with Earth's magnetic field. Once cooled below the Curie point, 585 degrees Celsius, this alignment becomes permanent and these rocks freeze in that direction, preserving the polarity of the field at the time. But here's the twist. Earth's magnetic field reverses polarity every few 100,000 years. During a reversal, the north and south magnetic poles switch places. So, lava that solidifies during a reversal becomes magnetized in the opposite direction compared to lava formed during normal polarity. Once scientists confirmed that these magnetic reversals had occurred repeatedly throughout Earth's history, they began constructing a magnetic timeline. By analyzing the polarity of hundreds of lava flows and using radiometric dating, they built a record going back millions of years. The longest periods of consistent polarity are called crons, each lasting about 1 million years. At the same time, oceanographers started mapping the seafloor using magnetometers, instruments towed behind ships to detect variations in Earth's magnetic field. One of the first major surveys revealed a surprising pattern. The seafloor was striped with alternating bands of strong and weak magnetic signals. Rocks with normal polarity enhanced Earth's magnetic field, while those with reversed polarity weakened it. Even more compelling, these bands were symmetrical on both sides of mid-ocean ridges. This symmetry revealed a powerful pattern. New magma rises at the ridge, cools, and locks in the magnetic polarity of the time, while older crust is gradually pushed outward in both directions. These discoveries proved that new oceanic crust is continuously created at mid-ocean ridges and pushed away in both directions. And because no oceanic crust older than 180 million years has ever been found, while some continental crust is over 4 billion years old, scientists realized that Earth's surface is not static. It's dynamic and constantly renewing itself through the movement of tectonic plates. More evidence came from hotspots, stationary plumes of upwelling magma deep in Earth's mantle. When scientists mapped volcanic islands and underwater volcanoes, called seamounts, in the Pacific Ocean, they noticed a long, straight chain of volcanoes. One of the best-known chains, the Hawaiian Island Emperor Seamount Chain, includes at least 129 volcanoes. Radiometric dating shows the volcanoes get older with distance from Hawaii. Hawaii itself is less than 1 million years old, Midway is about 27 million years old, and Suco Seamount near the Trench is around 65 million years old. This age pattern supports the idea of a mantle plume, a narrow, rising column of hot rock beneath the lithosphere. As the Pacific Plate slowly moves over this stationary hotspot, magma breaks through the crust, forming volcanoes. The age of each volcano tells us how long it's been since that location passed over the plume. Older islands drift away and become inactive, while new ones form directly above the plume. Hawaii is still volcanically active today. Its volcano Kilauea is one of the world's most active. Kauai, the oldest of the main Hawaiian islands, was formed about 5 million years ago. Its volcanoes are extinct and now show signs of heavy erosion, like jagged peaks and deep canyons. This volcanic trail is called a hotspot track, and it acts like a moving timeline, recording the direction and speed of the Pacific Plate's motion. To date, scientists have identified over 40 hotspots around the world. Some, like the one beneath Iceland, sit beneath spreading centers, adding new crust to mid-ocean ridges. Others may originate as deep as the core, mantle boundary, while some are much shallower. These hotspots offer independent confirmation that tectonic plates are not fixed, they're moving, reshaping Earth's surface over millions of years. Starting in 1968, the deep-sea drilling project changed everything. Scientists aboard the Glomar Challenger drilled into the ocean floor and studied the extracted sediments and rocks from the crust and below crust. What they found confirmed the findings from magnetic stripes on ocean floor. The youngest sediments were found at the mid-ocean ridges, and the oldest sediments were closer to the continents. Sediment thickness also increased with distance from the ridge. These findings confirmed that new oceanic crust forms at ridges and spreads outward, and that the ocean floor is geologically young and always being recycled, solid proof of seafloor spreading. All these clues, from rocks and fossils to magnetism and volcanoes, come together like puzzle pieces in Earth's greatest story. From matching fossils and glacial evidence to magnetic stripes beneath the ocean, the evidence for plate tectonics is everywhere. It explains volcanoes, earthquakes, mountain ranges, and even climate change over geologic time. Understanding it reshapes how we see Earth, not as static rock, but as a dynamic, living planet. If you enjoyed this deep dive into Earth science, hit like, subscribe, and ring the bell so you never miss a video. Got questions or want to explore more topics like this? Drop them in the comments below. We love hearing from curious minds like you. Thanks for watching. Stay curious.